Hey everyone. So we're going to continue our discussion with partition function and how it relates to things like Helmholtz free energy and come up with some equations, particular for pressure and ideal gas law stuff. Now, one thing I just want to reiterate was that I want to remind you that one of the things that we're doing is we're kind of recreating, reinventing the wheel, but we're coming up with equations for things that we've already discussed from previous physics classes, in previous thermal classes or even in chemistry. Now, I just want to kind of explain why we're doing this. Now, there are two ways to kind of get equations like the ideal gas law or this pressure equation. One way is through looking at the macroscopic view and looking at the microscopic process. Now, normally we develop everything through a macroscopic view because that's how we see the world. But unfortunately, if we encounter, let's say, scenarios that don't exist in what we normally consider, like for example, a two-dimensional space rather than a three-dimensional space, then it turns out that it's going to be hard for us since we don't have any actual experimentation uh, to kind of deal with that. But looking at it through a kinematic process, looking at the microscopic process, it becomes a lot easier for us to develop equations for two-dimensional spaces, one-dimensional spaces, and all these other variety of things that we could ever encounter. So I just want to kind of reiterate, if you ever wonder like what's the whole point of this, it's so that we have a deeper foundation, but also a way to kind of come up with these equations for things not within our observable universe, I guess I could say. All right. So before we discuss pressure, we have to talk about the two different types of processes. There are two processes. There's a reversible process and an irreversible process. Now, reversible processes are ones where a situation like compressing a gas or heating something up, it's done in such a slow manner, infinitely slowly, that we can consider that at every single moment, the gas is essentially at an equilibrium condition, meaning things like the ideal gas law are always existing throughout. So if you recall something like an isothermal process, so isothermal, the temperature remains constant. Now for a reversible process, it's done in such a way that first, the temperature throughout the entire gas is the same. And it's also done in such a way that pressure and volume are always going to be indirectly related. So doubling one always halves the other. Now we consider this as an ideal process because it makes it because it's something that doesn't really exist in nature. It's something that we can't really see. But the reason why we even think about using this and why we even care is because it makes life a lot easier when dealing with graphing and calculations to imagine processes being reversible. And what it'll do is it'll actually give us an upper limit to what we can work with. So, for example, a good example is when we start talking about engines and the efficiency of engines. We're going to look at reversible processes because if we can say an engine working at these conditions as a reversible process can reach an efficiency of 50%, then that means that any real engine working at those same conditions is going to be an efficiency a little bit less than 50. So it'll always kind of give us a rough idea of what we're working with. Now, irreversible processes are what we normally get in the real world. This is actually all real world processes are technically considered irreversible. Uh, they're done, irreversible processes are done in a finite time, so you end up getting a situation where um, every single state is in an equilibrium, and that the ideal gas law really only exists at the very first and very final stage. Um, and a lot of that comes from the fact that if you take a gas and you start, compressing it, then there are going to be some areas in there where maybe the pressure isn't always the same. Like that's one thing with gases is that just because we say, oh, the pressure is, some number of atmospheres, doesn't mean it's that uniformly throughout. There might be an area where it's a little bit higher. But also, if we just start compressing something, they might have a spike in pressure or a spike in temperature that makes it so that it's not always um, following the ideal gas law, but it will once it reaches that final stage. All right. Now we kind of ignored volume when it came to dealing with the energy in a system. So what we're gonna do is we're gonna look at a volume where it's being decreased from some original volume to some new volume, which we're gonna actually state as V minus delta V. Um, and we're also gonna say that it's gonna remain in its whatever state it was originally in. So our equation ends up becoming this. Um, E of S of V minus delta V gets us this. I think this is pretty much similar to something that we did in the last video, um, but this can be Taylor expanded into this format. Again, we kind of ignore the higher ups because the higher order derivatives don't matter. Um, and we know that if a force is being applied in order to actually compress this gas, that says an external force, then we know that there's work being done, and work is essentially the change in energy. So we can say that it's the energy from the new needed to get to that new state minus the original energy. And so going back to our Taylor expansion and bringing it in, we actually get this P delta V. So again, this is the same equation that we've gotten before, but we're looking at it through the kinematic process. So what we can get from here by relating those two equations are P delta V and the equation for the energy, we get this relationship that pressure is just the derivative of the energy state with respect to volume. And then we could define the average pressure as being this, the derivative of the average energy with respect to volume. So this is what we're going to have as our one of our first equations. So this is relating to how we could find pressure based on our equations for energy. Now, uh, I just want to reaffirm and restate something I've said before, that one of the goals that you should be looking at is using these equations to see how things are related. As I've said, what we're going to be doing in the class is I'll show you how things work in the real world, in our universe, where we would start, and then how the processes follow through. What you're going to have to be able to do on homeworks and on tests is understand that process, but and be able to do it at a different starting point. So again, I go back to the same thing where, right now we're in the three-dimensional world. Maybe I'll give you a multiplicity function in a two-dimensional world. In which case, what you'll do is you'll pretty much develop the same equations that we've just done. We have an equation that relates the multiplicity to entropy. We have an equation that relates entropy to energy, and now we have an equation that relates energy with pressure. So we're kind of linking all these processes together eventually. All right. So kind of going back to what I said before about how there is a relationship between energy and entropy. So now what we could do is we could take that equation for energy and pressure and rework it so now it's looking at pressure and entropy. So entropy, if it's a function of energy and volume, can be rewritten as this, as a partial derivative of the entropy with respect to energy and the entropy with respect to volume. Now, in the situation where we're considering that entropy is going to remain constant, because it said that before that it's remaining at its initial state. All we're doing is changing the volume. So that's going to tell us that this equation, this term right here, is going to end up being equal to zero because in total it doesn't change. So moving the things around, we end up getting this. And then what we can do is pretty much like divide both sides by dv to get this. And now you can start to see that where we've seen this term before and some of these other terms we've seen. So that first term, if you recall from the previous video, is 1 over tau. We just talked about the equation for pressure, so we could plug in pressure into that part. And this is the only one that we didn't really discuss, so we're just going to leave it as is. And now we have a relationship between pressure and the change in entropy. So for the most part, pressure is similarly related to the change in energy and the entropy with respect to volume. The only difference is now there's this issue of tau, where the other one didn't have one. Okay, so we could go back to the entropy equation and we could plug in pretty much everything that we have so far in order to come up with what's called a thermodynamic identity. So again, this was our entropy equation. This we could just simplify as the change in the entropy. We know what this term is, that's 1 over tau, and we now know what this term is, that's p over tau. So we can move the tau over to one side and move p dv over to the other side, and we get this. Now, one thing to note is that this is the first law of thermodynamics that you've probably discussed in physics 126, I believe, or in a previous science class. This is referring to the change in internal energy. This is the heat added to the system, and this is the work done by the system. So we just derived this equation using this whole concept of the microscopic states. It just looks a little bit different since we're kind of turning this into heat and this into work. So yeah, this is the first law of thermodynamics. You've probably seen it looking like this. So that's one thing that I'm going to try to keep showing regularly, is that a lot of the equations that I'm bringing up are going to be very similar and pretty much identical to equations you've done before, but they're now going to look a little bit differently, like including entropies and taus instead of, t's and q's and things like that. All right. Now, all this is going to bring us to the Helmholtz free energy. So the function for the Helmholtz free energy is being defined as this. F is representing the Helmholtz free energy, U is the internal energy, and this is the heat added to the system. So pretty much the whole point of the Helmholtz free energy is, as its name sort of implies, it pretty much is referring to how much useful energy we have within a system when held at a constant temperature and volume. You can almost think of this as being the amount of work that we could get out of the system. So if we go back to our scenario where the system's in thermal contact with some reservoir, then we know that the Helmholtz free energy will end up being a minimum value. So we end up getting this where dF is going to be equal to 0. And we can kind of show this by taking the derivative of this, setting this equal to 0, and seeing that we end up getting this relationship, something that we actually do know is true. So that does tell us that dF does have to be either a max or a minimum. Now, if the temperature isn't held at a constant, so like if it's not in an isothermal process, if it's changing through whatever we do, then when we take the derivative of the entropy part of the heat part, we have to split it into the two sections, and then what we can do is we can actually combine this into negative P dV, the work part. Um, so we can actually come up with two slight different variations. If we take the Helmholtz, the partial derivative with respect to temperature, then it's going to be equal to negative of the entropy. If we take it with respect to volume, then it becomes negative pressure, just by looking at whatever's in the coefficient part. All right. Of course, these subscripts right here are just representing to tell us what's remaining constant during that. So the volume has to remain constant for this one so that this term becomes zero. And for this one, the temperature has to remain constant. So this part goes to zero. All right. If we go back to the isothermal process, looking at the free energy differential, if we go back to what we said before about how the partial with respect to V is equal to the pressure, then if I divide this entire differential by V, take the derivative with respect to volume for each one, then what I end up getting is that the pressure is equal to this plus this. Each one of these being divided by V. From there, again, I have equations that deal with these. So yeah, it pretty much combines the two equations that we got from the pressure, from one related to the internal energy and one related to the heat. So yeah, this is actually leads us into discussion that there's two different types of pressures. There's an energy pressure and an entropy pressure. Mainly, it turns out that each of these pressures pretty much becomes dominant in a different scenario, which for the most part does kind of make sense. So, for example, in things like solids and liquids, this term would end up being the more dominant one, the energy pressure, while this one would be more dominant in gases. Mainly because with gases, the entropy would be significantly higher because a gas typically is more chaotic. All right, so this video unfortunately is going to be a little bit on the longer side. I apologize. There's really not much that I can't really break this up because I'm just constantly going back and continuing with the Helmholtz free energy. But what we can do is take our Helmholtz free energy equation and the entropy equation that we have in order to actually get this relationship that the energy is equal to this. Now, this can only be true if this is true. Something like F over T equals negative ln Z, based off of some of the other equations that we have for U. So what we can say is that another way that we can find the Helmholtz free energy, besides looking at the energy, besides looking at the entropy, is by looking at the partition function and stating this, that the Helmholtz free energy is equal to negative tau times ln of Z. So again, the whole thing, the whole point of all this is to kind of come up with as many equations that interlock with each other. We're trying to develop a web of equations that link from one term to another, so that no matter where you start, you can pretty much find any other scenario. If you start with the partition function, you can go any way to find any other equation. Or if I give you the Helmholtz equation, you can find anything else. So that's pretty much what all this is. It just keeps developing more and more equations to kind of fill up a web of relations. All right. So this actually allow us to rewrite the probability as related to the Helmholtz energy. So yeah, that's what this is. Just taking this, raising the terms to the e to get another form of the partition function, and then combining that to our equation that we have for the probability. Remember, the probability was that Boltzmann constant divided by the partition function. So that's what this is. This is nice because it kind of gets rid of that summation term. So again, different varieties, same old, just written in a different way. Tomato, tomato. All right. I guess I'll just throw this in there. We'll talk about the ideal gas law and the whole concept about ideal gases. Now, I'm just going to kind of breeze through this first concept, mainly because of the fact that it kind of deals with a little bit of quantum, and I kind of want to avoid that as much as possible. So I'll just say this. The scenario that we're going to look at is one where we have an atom that is within a box. Now, the atom's going to have some known mass, m, and the box, just to make our lives easy, is going to be a cube with sides L. Now, there is an equation for this. The energy can actually be found using Schrodinger's wave equation. Now, if you don't know what that is, again, don't worry, because you shouldn't have to do much with this. I don't think you. I think I try to avoid it as much as I can. But mainly, this is going to be used to develop some other things. So you shouldn't have to reuse this stuff. But you end up getting this weird equation where this term, this phi, is the Schrodinger's equation. Um, where it, yeah. And then we have these terms nx, ny, and nz, which are just positive integers. Now, the energy based off of this is defined by this. And this is pretty much the only reason why I bring up the Schrodinger's wave equation. Um, Actually, this wave function, I should say. Um, so the energy at pretty much any orbital state is going to be equal to this. This h bar is, I think I don't know if I mentioned that in this class, but it's a variation on Planck's constant where it's just h divided by 2 pi. It comes up so much that they just kind of simplify this as being h bar. So that's all it is. Now, as we know, the partition function is taking the energy states and summing it across all the states. So it's that e to the negative epsilon over tau. So we're taking the energy based off of the Schrodinger's wave equation and plugging it into here and then summing it across these three variable states. Now, what we can do to make our lives easy and to simplify it is turn this into a triple integration. So we end up getting this, and then we're going to take all these constant terms like the h bar and the pi, and replace it with an alpha like this. So now we end up getting this equation. Now, one thing that we can do is each of those dimensions. Well, first off, actually, I guess I could say that the e to the negative. Let me just actually take a step back. So what I can do is I could separate this into three terms: an e to the negative alpha squared nx term, e to the negative alpha squared ny term, multiplied by an e to the negative alpha nz term. And then I can say, well, the nx term doesn't matter for these, but it will be here. So I could pull them out into their own respective parts. And then the last step is to say, well, nx, ny, and nz are pretty much the same thing. They're just values for x, y, and z direction, but they're just integers. So if I'm summing from 0 to infinity across each of these values, well, it's pretty much going to be the same thing. The equations are the same, so I can just replace it by saying I'm only looking at one dimension and then cubing it. Now I want to take a quick break and say that uh, I had mentioned before that one of the things that we do is look at, well, what if we have different dimensions? What if we're looking at a two-dimensional case? Well, everything that we've just done pretty much holds true until this point. Instead of it having raised to the third power, because in this case that we're doing, we're looking at a three-dimensional case. If we were instead looking at a two-dimensional case, there would be no z direction, so we'd only have an xy, an x and an xy. So this would actually become 2. So you'll notice that like I said, the process still ends up being very similar, and we end up getting things that kind of will be working the same way. The only difference is what we start off with. There will be so in a two-dimensional case, something like this would be slightly different. But once we get to here, then we can kind of reorder this and look at this again and basically realize that this can be simplified to look like this. And then this has a known integration. It's given like that. Rad pi over 2 alpha. All right, so taking it back, replacing our alpha term back into here, we end up getting this right here. And then what I can do is L cubed. Well, that's just the volume of the cube. And then this term I'm going to replace with NQ. And then I'm going to define the volume as being 1 over n. So just to explain exactly what some of these terms are. As you know, V is volume. N is actually being used in this term to refer to what was it? Concentration. That's it. I was thinking of the word C, but for some reason the word concentration wasn't coming in, and I was instead thinking of a different C word that sounds very similar. So I apologize for that. So N is actually referring to the concentration, basically the number of molecules per volume within it, and then NQ is referring to the quantum concentration. The quantum concentration, what this is going to do is essentially tell us is at what point will a gas be undergoing quantum effects? When will we start reaching a realm where we have to start worrying about quantum interactions between particles? So if the value of n is lower than the quantum concentration, then we can treat this as a ideal gas that has no quantum effects. So that's pretty much what the NQ is for. It's a check to make sure that we don't have to worry about any extra things going on. So we can actually bring up something called the de Broglie wavelength. For those who don't know, de Broglie was a mathematician. I believe he actually was fighting in World War II, maybe when he came up, maybe not World War II, but one of the World Wars when he came up with this idea. But he was the person who kind of realized that matter particles exhibit wavelength properties. Ironically, by taking the equation for the momentum of a wave and the momentum of a particle and setting them equal to each other. So that's what this is. It takes the momentum of a wave and sets it equal to the momentum of a particle, and that gets us the wavelength of matter based off of their speeds. So if we want to rewrite it in terms of things that we've been dealing with, we'd end up having this: h bar over m times the average velocity. This can actually be rewritten as this: square root of m tau. And then from here, what we could say is if we cube both of those terms, we end up getting this. And this is pretty much equivalent to 1 over NQ. So what this kind of tells us is that the whole quantum concentration actually relates fairly closely with a particle being within a cube that ends up having sides that are equal to the de Broglie wavelength of it. The idea that what we can almost consider is that if the object gets concentrated enough so that they're close, very close proximity to each other, we can pretty much separate all the particles as being in separate independent cubes that don't overlap, and that we get into the quantum concentration realm once that cube gets small enough that it ends up going into the until it has the sides equal to this de Broglie wavelength. Uh, it also makes sense because that kind of seems that makes sense with what we know about waves and how things don't really happen until we get to sizes relative to their wavelength. Like for example, diffraction. Diffraction is not really noticeable unless we have openings that are roughly within the same range or a similar range to the wavelength. Otherwise, there would be no visible diffraction. So it pretty much kind of goes back to that same idea that we won't really get this quantum effect and we won't really get these wave properties of these particles unless we start getting to sizes relative to their wave properties. All right. So this just kind of explains what I said before about how as long as the particles are separated by their de Broglie wavelength, then it's not in the quantum concentration. That the quote unquote imaginary box surrounding each of these particles is bigger than the de Broglie wavelength. And we can actually consider it being in what we would normally think of as the classical regime, the ideal gas, the you know normal macroscopic process. But once that concentration gets large enough so that the distance gets small enough for their wave functions to start to overlap, then we end up entering into the quantum regime. Now we're going to define ideal gases as being specifically in the classical regime. And we're also going to put in one extra caveat that they're non-interacting, that each particle remains independent relative to the other. So, coming up with some more equations for the ideal gas and kind of relating it to some of the things that we have already. So now that we have an equation for the partition function, well, now we can redevelop a lot of these equations in these new terms. So for example, the average energy was given through this, the weighted sum of the energy across all states divided by the partition function, which we already know can just be simplified to be written like this. So now that we know what Z1 is, we could plug that in and take the partial derivative with respect to tau, which is this term right here. So what I did here is I actually separated everything into one term dealing with that were constants, and the one term dealing with tau. So we end up getting this. And then when we take the partial derivative with this with respect to tau, this whole part goes to 0. And then we're left with this. And then, really quickly, you may notice that the exponent above the L went from 3 to 2. That actually is intentional. If you notice, this is to the 3/2. So if you actually bring this back into the ln function and distribute it throughout, then this will go back to being L cubed. So it was done so that it can be brought in with all these terms. So I just want to kind of reiterate why I did that. All right, so back to here. Now we know what the partial derivative is. We could take this and bring it back into our equation for u, and we get this 3 halves tau. Now, one thing that we want to do is, since we have an equation for energy based off of the ideal gas, we can actually now kind of relate this to our original equation for internal energy, which, if you recall, was 3 halves kT. And remember, tau is being defined as kT. So this equation and this equation basically are exactly the same. And like I said, we're redeveloping these equations and showing how we can take these complex setups that we have for any sort of distribution, and relate it to what we normally see for the ideal gas by using these partition functions. So yeah, this is the energy per atom. So same thing that you've done in previous classes. All right, so we'll work on this question. Pause the video, work on the self, and we'll go over in a second. All right, so we have a gas set up like this at STP, and they want to know the concentration and they want to know the quantum concentration. So in order to find the concentration, I need to figure out what the volume is. So at STP, we know that for each mole, the volume is defined as this. Now, if you didn't know that, one of the things you could have done is the ideal gas law. Of course, we haven't technically come up with the ideal gas law, but you should know it. PV equals nRT. And you can come up with the equation using standard temperature and pressure. We also know that within 1 mole, there's this number of molecules. This is Avogadro's number. So the concentration is just going to be the number of molecules divided by the volume. That's literally what concentration is. And so we end up getting this. Avogadro's number versus the volume. And we get that the concentration of this gas is equal to this, 3 times 10 to the 19 molecules per centimeter cubed. If you want, you could have always converted that back into meters cubed. The quantum concentration, what we're going to do is we have to figure out what the mass is. So with the 28U, we just multiply it by the mass of a proton. And then what we can do is just plug and chug into the quantum concentration equation. So plug all the numbers in, and we get this. Because the other number was relative to centimeters cubed, I'm just going to rewrite it into centimeters cubed here. So this is the quantum concentration. So I think... Yeah, I think I made a little mistake in my writing. So our current concentration is 3 times 10 to the 19th. And in order to get to the quantum realm, we would need 1 times 10 to the 26th. So basically what we would need is 3 times 10 to the 6th times more molecules per gas. Of gas per centimeters before we get to the quantum realm. So we would basically need to take the concentration that we have now and multiply it by, I believe that would be 3 million. So it's 3 million times more concentrated than the original case. The way it's written right now makes it seem like I would just need to have a little bit less than a mole more of gas, and it's all also concentrated. But no, it's times molecule. So, like I said, about 3 million times more molecules in order to get into the quantum realm within that same volume. All right. So one thing that we could do is we can kind of rewrite this equation. That partition function was really only for one particle. We can expand this by looking at n particles, but then setting it up so now it looks so we set it up as n systems, if you will, each with one particle. This is very similar to what we did with the ensemble, if you recall. One of the things in the previous class videos where we talked about this concept of an ensemble, where we look at all the uh, different states that could be available, and we consider each state as occurring at the exact same time in systems that are acting at the same uh, uh, time. So what we do here is pretty much the same thing. Each particle is inside of a box, and that they're just, because remember, they're not interacting, so it doesn't matter whether we have 15 particles within one box not interacting, or one particle, 15 boxes each with one particle not interacting. So as we know, the partition function is just going to be the product of all these partition functions. Um, so what we would get is we'd have to include a correction when we do this, but this ends up just being z1 to the n divided by n factorial. And we actually know that z1 is just nq over times v. So we end up getting this as another way of writing the partition function for n number of particles. Again, we can come up with an equation for the ideal gas law, for the energy equation that we had before. Same thing, now we have this n term. Again, it's literally the exact same equation that we've done for that you've done in other classes. The free energy equation, if you remember, it was equal to negative tau ln of the partition. So bringing that in, we end up getting this. Of course, now we have this factorial that we have to get rid of. So what we can do is do the Stirling approximation for this. So plugging in our term for z1, we get this mess, and then the Stirling approximation simplifies to this. And from there, we can actually combine a lot of these terms. Like we have a tau n over here, tau n over here. So this actually can be brought into here. We can find the pressure using this. So take the pressure, use this equation, take the partial derivative with respect to volume. The volume is pretty much only seen right here. So this term drops to 0. This just becomes 1 over v. And hey, look at that. We get PV equals n tau. Remember, if we rewrite this in standard classical terms, this is PV equals nkt, which is the ideal gas law. So, like I said, redeveloping all these equations that we've gone before. We can come up with an equation from the Helmholtz for entropy. So that's what this is. If you are wondering why I haven't combined that in here, it's just going to make life a little bit easier. But realistically, this could easily be brought in. In fact, if I do bring this term into here, then this is going to simplify into being a term of concentration. So it would actually end up simplifying to being the quantum concentration over the concentration, I believe. But when we take the partial with respect to the temperature is only in this term right here and this term right here. So what you can do is, you have to do the chain rule, derivative of this. Oh, well, actually we have to, and right here, I forgot this term. So we take the derivative of this plus the derivative of this one plus the derivative of this to get this whole thing. Yeah, so here, I'm starting to combine it over here. So combining, bringing this over to here, and simplifying it, moving some things around, we end up getting this as an equation for the entropy. And this is actually given a very special name. Unfortunately, I don't really know how to pronounce this name that well, so I'm going to call it the Sackur-Tetrode equation. I know that's definitely not really good. But this is an equation that only works for monatomic ideal gases, mainly because of the fact that that equation that this three halves that we have over here and over in all these other areas, this is actually relating to the amount of degrees of freedom that were provided. Monatomic gases are only allowed 3 degrees of freedom, movement in the x, y, and z direction. Uh, so if we instead are dealing with diatomic or triatomic, where we're now allowed for higher levels of degrees of freedom, like rotational and vibrational, then this term will actually end up changing. I believe it goes 7 halves and 9 halves, but I might be wrong on that. I'm pretty sure we go over it in the future. All right. So here, just playing around with the equation. So pause the video, work on the stuff, and we'll go over it in a second. All right. So they give us a bunch of numbers. They want us to use that entropy equation that we just found. So, nothing crazy. We can take these numbers, plug them straight into the quantum concentration equation to get our quantum concentration being this. We can use the number of molecules in the volume and pressure over temperature to figure out the concentration, which is given by this. Notice we are in the classical realm. And then just plug and chug. So we end up getting that the entropy is given as this equation. For part B, they want us to compare this to the entropy of helium gas under the same conditions. So one thing that we could do is we can redo the calculations. Another thing we could think of is what exactly would be different about a helium gas versus the argon gas. And for the most part, every single one of these terms would be the same except for this mass. So we can actually go back to our equation and think about where's mass. Well, mass is in the numerator right here. And so that means that increasing the mass would increase the quantum concentration. Increasing the quantum concentration would increase this term, therefore it would increase the entropy. So my guess would be that the entropy would end up being higher. Oh, sorry, lower. Oh, right. If the mass increased, then the entropy would be higher, but I made the wrong assumption in my belief that helium had a higher mass. Somehow I thought 4 U's of helium mass is bigger than 40. My mistake. But the reasoning was still the same. Like I said, going back to that equation, looking to see how you change mass, how would that affect the quantum concentration, and how changing the quantum concentration affects the entropy. And like I said, another thing that you could actually do is you could take the equation, and this is something that I actually like doing, is take out the one term that's changing, that's variable, and move all the other terms to one side. And then what you can do is take all of this stuff and just combine it into some constant term. And then from here, you can actually see, oh, if I change the mass, I quickly change the sigma. So this would be something that would be nice to do on a test, because it really does give you a much stronger explanation behind it, rather than just saying, oh, increasing mass increases entropy. Like, you'd want to kind of give a little bit more explanation. So entropy goes down when the mass goes down. Unfortunately, my original explanation assumed it went up. So here's the next question. Pause the video, work on the stuff, and we'll go over in a second. All right. So we have here that the object is confined to one-dimensional, length L, and they want us to find the entropy. And they also say that the particles have zero spin. So when we think about where did we start off, think back to what we did with our three-dimensional case. Well, we started with this equation before. Now remember, our equation was a little bit different. We had the L cubed over here, and then we also had this term being across x, y, and z. Well, what I can do this time is I can actually rewrite this where it's only now one dimension, a single length, and only one set of integers. And then what I can do is, again, very similar to what I did before, I'm actually going to combine all this into a single term like this, epsilon 1, n squared. And then I can also set it equal to this so that when I do the partition function, this will just simplify to this alpha n squared. So that's all this is doing. And then from here, I can look back to what I did before. And this is actually something that goes to this term right here, rad pi over alpha 1/2. From there, I can actually plug in what alpha is back into the equation, and I end up getting this. And this all simplifies to this. So very similar to what we had before, where it was volume times the quantum concentration. Here, though, it's now length times the one-dimensional quantum concentration. That's why I'm kind of adding in this 1 here, just to kind of keep reminding myself that this is not the same NQ from the previous slides. Now, again, going back to what we had before, if you remember, the Helmholtz free energy was given by taking the ln of the partition function across all the particles. So this is for one particle, this is for multiple particles. So that simplifies to being like this. Again, we have to do the Stirling approximation. Remember, it's literally the same thing that we've done in the previous things. So our free energy is given by this relationship. And then what we can do is to find the entropy, well, we take this Helmholtz and take the partial derivative of it to get this. So this is what the partial will end up being equal to. This stuff will actually simplify, and we end up getting, there it is. This would be the simplified. So it ends up looking something like this. So again, this 3 is slightly different from what we got before, mainly because of the lack of degrees of freedom. All right. Another thing that we need to talk about is the equipartition theorem. So this kind of goes back to something that I said before. So I kind of kept hinting at it. So I kept hinting at this, that the 3/2 comes from the fact that there are 3 degrees of freedom. And basically the equipartition theorem says that for each degree of freedom, you have essentially 1/2 tau of internal energy for each particle. So when we have, if we go to a diatomic particle that now is allowed rotational energy, there are 2 more degrees of freedom based off of how it rotates, whether it's across the minor or major axis. So that means that this 3/2 for a diatomic particle would turn into 5/2 because of the 2 additional degrees of freedom. And then if we go to triatomic, where now there's vibrational energy, that goes to, again, an additional 2 more, going to 7/2. Now, another thing that it could mention, I just wanted to actually point this out because this does come up a decent amount, is that you might be given a scenario where you're not dealing with the monatomic gas. That you are still dealing with the you're not dealing with the monatomic gas. You're dealing with the diatomic or a triatomic gas. But what they'll say is that it's a low energy diatomic gas or a low energy triatomic. And usually, what they're doing in those cases is they're trying to hint that we're still only limited to these three dimensions of translational degrees of freedom. So I just wanted to point that out there that if you end up seeing a question that's dealing with diatomic particles, and all of a sudden you're assuming that the coefficient turns into 5 halves, but the question, the answer, and the work still dealing with 3 halves. That's because of this addition, this fact that it's could be at low enough energies where it's only allowed to move translationally, but not yet excited enough to start rotating or vibrating. All right, so this is a typical graph that they show. So again, you can see it here that the temperature will affect whether or not a diatomic plus gas will actually start reaching different values of energy. So if it's below, 100 Kelvin, so like I said, a low energy state diatomic gas, it would still only deal with translational. But once you start going to higher temperatures, then it would allow for additional degrees of freedom depending on the temperatures. I would say that they probably wouldn't give you a number and have you guess. They would usually call it low energy or high energy. And they might even add in additional information to kind of hint, like only allowed translational or only allowed vibrational. All right, so here's a practice question. Pause the video and work on the second. We'll go over it. All right. So what we have is this. We want to show that this is equal to this. So this is called the mean square fluctuation. Basically looking at the difference between the value and the average and then squaring it. Essentially, it's pretty much the standard deviation if you want to think of it like that, except, with the square addition. So yeah, what we're going to have to do is first expand this. So when we take this, we end up getting is this, the average of epsilon squared minus 2 epsilon average epsilon plus the average epsilon squared. Now, the one thing that I want to note is that when we take this average, we have to be careful where this average is going to. Like, for example, this term. This term isn't being averaged, it's being squared. So when I average, it's actually going to occur after the squaring term. Here, I don't have to, this isn't being averaged, so this could just be thrown in there. This term's already averaged, so I don't have to worry about that. And then this term, again, is being averaged already before the square. So that kind of drops out. So this actually turns into looking like this. Now, this is different than this. So this would be like if you had a bunch of numbers with negatives and then you square it before you take the average, versus here where you take the average with the negatives and then you square it. So if you don't believe that, you can actually test that out yourself. But from here, we can actually say that this average of epsilon times average of epsilon is actually epsilon squared. So we end up getting minus 2 average epsilon squared plus average epsilon squared, which just gets rid of this 2 here, and we end up getting this. So this entire function, this mean square fluctuation, actually just becomes the average of the epsilon squared minus the square of the average epsilon, if that kind of makes sense. It's a little bit weird. Going back, we know that the average energy is defined by this. And we know that we can simplify it to this case. So this is going to deal with this term here. Now for this term, I do the same thing. I just add in squares. So this becomes a square there. This term doesn't change because this is just the probability. And this doesn't change either because that's what it is. That's the partition function. It remains constant. And then doing something similar to what we did up here, well, this is just me taking the derivative of this stuff twice. So I end up getting this term. So this simplifies to this, and this simplifies to this, the second derivative. So going back, I can then say, well, this gets brought into this first term here, and this squared goes into this term. So I end up getting this relationship. Now, I'm defining beta as being the 1 over tau, something that some other books will actually deal with. So just doing a sort of substitution here for the partition function so that it's in similar terms. So this part, I'm just going to work with this and actually try to get it to the same midpoint that I have. So the way I'm doing is like a pincer process. I'm taking this, moving it one way, taking this, moving it towards here, and I'm going to meet in the middle. So from here, this can be split up into a delta U over delta beta and a delta beta over delta tau. This from my relationship right here is just 1 over tau squared. So that drops out those. And so I end up getting that this term can actually simplify to being like this. So now going back to what I had before, I can rewrite this since I have that energy. Because remember, U is actually being defined as the average energy. I can take what I had for the average energy from before and just take the partial derivative with respect to B right here. So I'm doing a little bit of math. I separate across the two parts to get this. So this ends up changing to look something like this. And you may now start to see what's occurring. So this term should start to look familiar, and this term should start to look familiar. So if you recall from before, we had this, and now with this term, I have this term, which is exactly what I had up there. So, I compare them, and I could say, well, since this equals to this, then that means that this relationship holds true. All right. I know that was a little bit rough, and like I said, this video is getting long, so I'm just going to say these are the summaries of all the things that we talked about, the partition function and how it relates to pressure, probability. We came up with new equations for pressure, and we also came up with this Helmholtz free energy. We also came up with all these other equations for things like concentration and quantum concentration for ideal gases. And then this is the homework for chapter 3. If you have any questions, please let me know. Otherwise, I'll see you later. Bye.